radians, that's the angle, in the same, and whatever the time is. This right here is just omega. It's the angular speed. So we have this relationship of V equals omega r. So if I have, so as I move around like this, how fast my arm is moving depends on where I am, and the farther I am from the radius, the faster it's going. As r goes up, V gets bigger. Assuming omega stays the same for everything. If my arm stays rigid, it's all has the same angular velocity, angular speed. All right, back to the derivation. I have a door that is rotating. I know a formula for kinetic energy. What speed do I use for the door? Or if I wanted a crude approximation, what speed should I use for the door? Let's do some numbers. So we got that, 10 seconds. All right, so we'll just take this. This is traveling at 6.28 meters per second. This is traveling at 0.0628 meters per second. Let's just, for the sake of this, assume that A is at the tip of the door. So 1 meter wide, which probably isn't too far off. Which speed do I use? Or what combination of those speeds? I know the speed at the middle is 0, so that's going 0 meters per second. This is 0.0628 meters per second. This is 0.628 meters per second.
Would it matter which one you use since it's the same object?
You'll get very different answers if you use different values.
Would it be A because that's like the maximum?
All right, so pick the maximum is what you're saying?
Yeah, because it's like the furthest it traveled.
The trouble with that would give you definitely an upper bound here.
Mm-hmm.
Because you have the mass of the door, and then whatever, you took your maximum speed, you would get the maximum possible kinetic energy.
Uh-huh.
But it's gotta be less than that because this isn't traveling quite as fast here. So let's go with that for right now. All right, so let's give it a mass, some nice number. Let's go with 5 meters, no, sorry, 5 kilograms. So the door has a mass of 5 kilograms. So the kinetic energy of the door, at least at a crude approximation, it's 1/2 times 5 kilograms times, you wanted to pick the outer part, 0.628 meters per second. If someone would be kind enough, squared.
.98596.
Anyone else got that? Got the same thing? All right, units?
Kilogram.
Joules. There was another response?
I said kilogram meter per second.
Don't forget we're squaring this, so it'd be kilogram meter squared per second squared. So a joule or a kilogram meter squared per second squared. All right, but I know it's gotta be less than that. Because again, that was the maximum speed. Suppose we took the middle, took the lowest speed. Right there at the hinge. What's the speed at the hinge? this is at point A, and this is axis of rotation. What is the speed at the axis of rotation?
0.0628.
That's
I mean-
0.1 meters off of it.
0.628 meters. Wait, what are? No.
At the hinge.
Oh, zero.
Yeah, 0.
Zero.
All right, so we've got, if we went with the upper level, we have almost 1 joule. If we went to the least, we have 0 joules. So the real answer is somewhere in between there. What would be a crude approximation for the actual value?
Would you just divide the first number in half?
In other words, the average of
Like
the
the
two?
average.
Yeah,
of the two?
all right, so that could give a crude approximation there. So if we did the average, so 0.49298, something like that.
Yeah.
But it's still a rough approximation. So we need to somehow figure out a way of dealing with that. We can get slightly better approximation if instead of we're thinking about it as two objects, as one object, we think about it as two objects. So if I took my door, I got the hinge here, and I think of it as two objects. At this point, this is traveling 6.0628 meters per second. This is traveling 0 meters per second, and in the middle would have to be between those 0.0314 meters per second. So I know that the kinetic energy, well, I have half the mass now. So I got 1/2 times 2.5, because I have half the mass, times 0.0628 squared would be here. This would be 1/2 times 2.5 times 0.0314 squared, and that would be 0. That would be 9298. $49298.
Mhm.
This would be 0.24649.
Would the first one not have 2 zeros before them? Like
Oh.
0.00?
Whatever.
Am I doing it wrong? I did 1/2 times 2.5 times 0.0628 squared.
Oh, that's my mistake. That should
Okay.
be 0.628, and that should be 0.314.
Oh, okay.
So if I went through the same thing right there and I took the average of those two, let's say 0.49, 0.25, so roughly 0.32. The average of these would be roughly 0.12, and so the sum would be 0.44 joules. So we get a slightly better approximation, right? So this was a crude approximation, thinking of one object. We've now broken it into two different objects, so we have a slightly better approximation. And we could keep going.
No.
Say it again?
I said no.
Well, we're gonna get away from specific numbers. Now comes the actual derivation.
Okay.
So just prepare yourself mentally for seeing a derivation. What we're doing is I'm saying that the kinetic energy of it is the sum of the kinetic energy of each little bit. I equals 1 to however many parts we break it up into. Just like over here, we had broken into two parts, and so I had two kinetic energies, just added them together there at the end. Now, in calculus, you're gonna let this in, you're gonna break it up into an infinite number of pieces. That is gonna be equal to the sum, and it's gonna go from 1 to n. I'm just gonna write I down here. Eventually I'll probably stop writing I, but It's this repeated again. This sigma right here, this capital sigma means we're adding. So this would be, well, actually, usually do it in the reverse order. The kinetic energy of the first part plus the kinetic energy of the second part plus the kinetic energy of the third part plus until we get to the kinetic energy of the nth part. That's all that this means, is that we're just adding a bunch of kinetic energies. So each kinetic energy is 1/2 mv squared, so this is 1/2 times the mass of whatever tiny part that is, so mass 1, mass 2, mass 3, times the speed of that part squared. So this just means that I have 1/2 m1 v1 squared, so it's the mass of whatever, I'm breaking it into small pieces, and this is just the mass of that first piece times the speed squared, plus 1/2 times mass 2 times the speed squared, plus so on until I get to the last piece. Now 1/2 is common to everything, so I'm just going to pull 1/2 out. It's basically factoring. So I got 1/2 times the sum of mi vi squared. Doesn't really look any simpler than what we were doing. We will eventually get to a point where it still doesn't look any better, but it actually is. Now I know that everything in this, we're assuming a rigid body, everything has the exact same angular speed. It goes to the exact same angle in the same amount of time. So instead of v here, I'm going to stick in my equation, which we had written, oh, there we go. V is equal to omega r. So this is equal to 1/2 times the sum of the mass of some part of it times omega r squared. Now I did not have a subscript next to omega because omega is the same for everything. So every term, so this basically becomes 1/2 m1 omega r1 squared plus 1/2 m2 omega r2 squared, that's r, plus and so on. Since I'm squaring omega and r sub I, omega gets squared, so this is, we're close to the end, 1/2 m sub I omega squared r sub I squared. Omega squared is common to everything, so I'm going to factor that out. I'm left with 1/2 omega squared times the sum of all those tiny little m sub I r sub I squareds. This is the point where we are almost at the end, but it doesn't look any better. We still have this huge sum. We break it up into n pieces, and we're adding them all up. Or calculus, we break it up into an infinite number of pieces. Each one has an infinitesimally small mass. However, this is better because this right here, that is the moment of inertia. Now you might be going, okay, great. Well, moment of inertia uses the symbol capital I. So what I'm claiming here is that kinetic energy, if everything has the same speed, boom, done. But if it's rotating, not everything has the same speed, and the kinetic energy is 1/2 I times omega squared, which is the formula we had on the board the other day. Now you might be still looking at this and thinking, well, that doesn't really help, because how am I going to figure out what I is? Well, it just so happens that for certain shapes, page 138 in the textbook, they've already done the formulas for you. So as I look at this, I see a stick rotating about its center of gravity. So basically, if I have a rod rotating about its center right here, there's a formula for it. 1/12 ml squared.
And L is the length? Is that
L is
what-
the length, yeah. So I for rod about center. Rod rotating about central normal axis. You know, it's a long skinny thing rotating about the center there, like that. The formula is 1/12 ml squared, where L is that length right there. So let's say I had this rod, I'm spinning about the center. Mass of 5, so I get 1 kilogram. The length will make 4 meters. So the moment of inertia of that rod is 1/12 times 1 times 4 squared, which is 4/3. Just simple plug and chug. Or 1.333 and so on. But what are the units? And not that it makes it any better, but there's not a one-word answer for this. What are the units of moment of inertia? Think about what are the units of this and the units of this. And don't forget we're squaring this one.
Kilograms, meters, squared?
Yep. Kilograms, meters, squared. So if that rod is rotating about its center, let's say that it rotates at 0.75 radians per second. No, that's not really gonna help a lot. Well, we'll stick with it. So if it's rotating 0.75 radians per second, so that would be roughly like that. Then the kinetic energy, 1/2 times the moment of inertia, 1.3 repeating, kilogram meters squared, times omega, 0.75 radians per second squared.
What's the symbol for radians? Or the?
The symbol for radian?
It's rad. Okay.
Yeah.
Rad.
And since we had not done radians before, if I remember, I'll show you an even simpler way of doing radians, of expressing radians. 0.75
Yeah.
units.
Do the meters per second cancel out? No.
I've got kilogram meter squared, I have
Oh.
radians per second
Squared.
squared.
So. Kilogram meters per second. No.
No,
Kilogram
we're squaring
meters.
the meters and squaring the seconds. Or, we just found kinetic energy.
Joules.
What happened to the radians?
Joule radians. Joule.
Squared?
Joule rad squared.
Joules, that's fine.
Okay. What did happen to the radians then?
Yeah, let's talk about what happened to the radians. We'll start with V equals omega R. All right, V equals omega r. This is something traveling in a circle. This is the speed, the linear speed at any point, and the angular speed.
So I'm sorry, you just happened to give us the omega, right?
Yes, I gave that to you.
Okay, so like in that kind of problem, you would just give us omega.
Or I would tell you how long it took to actually go around in a circle.
How long did it take to actually go around? That's how it
Because
would be.
omega, angular speed would be the angle it goes through for, if it goes around once, that's 2 pi radians over however much time it took to do that. So 2 pi divided by time is omega.
Okay.
Speed is just distance over time. Angular speed is angle over time. Times r. It's the same amount of time, so I'm just going to cancel that out. So what I'm left with is this distance is equal to angle times r. Okay. So if I have something that's traveling around in a circle, so it's going from here to here, the distance it traveled would be this, and I'm just going to use an s, it's same as delta x. That's the angle, delta theta, or just say theta. And that's the radius. So what we have here is that the arc length, that's distance around the edge, is equal to r times theta. Assuming theta is in radians. If we solve for theta here, so in other words, I'm going to take r over to the left-hand side, and the way I do that, since there's multiplication, I have to divide by r. So theta is equal to some arc length, some length, divided by r. Now let's look at units. The units of theta, we know as radians, would be equal to the units of the arc length divided by the units of the radius, which would be meters over meters. And what's a meter divided by a meter?
A meter. 1.
1.
Okay.